The most challenging part of setting up the runs for regular PanelPlex is just getting the list of all of the SNPs. And these are SNPs and indels, by the way. We allow for specifying, we call the location of the SNP or the indel, the junction location. And we specify a J-min and J-max for the junction min and junction maximum in order to allow us to specify a SNP site or indel. So for example, the first row of data here is data we got from the COSMIC database for chromosome 17. There's a SNP at position 952. So since it's a SNP, we put the same value in for both J-min and J-max. All right, here's a different SNP at the same location. Here's a third SNP, 3 nucleotides away at 955 here. So that SNP is close. It's too close. We couldn't design 2 separate PCRs in a reaction that at the same time would be able to separately amplify something at 952 and something at 955. They're only 3 nucleotides away. So all 3 of these targets that are highlighted in yellow are targets that we would combine. We'd make a new J-min of 952 and a new J-max of 955, include all 3 of these. The program does that process of combining the assays automatically. It recognizes things that are close. So all the ones in green are also a group. They form a group that are too close to have separate assays for each one. You can see in this case they go from 3,966 to 4,008. So they have a range there of 42 nucleotides. So that's not big enough for a separate amplicons. All those cluster of SNPs. I'm showing you this on a version that we have in our development version of it because I want to show you a particular feature of PanelPlex when we get to it. You guys, all the people in the conversation today are users of PanelPlex, so you guys all know how to log in and choose a genome, like the human genome. Here we go. Use the human genome as my target, no problem. So we'll go to regular PanelPlex here, right on the one that all of you guys use. Use the human genome as the target and hit next here. So typically you would give this a name like, HER2, HER3. I'm going to do a little assay on that. Now, we have a number of choices here. We can choose to do a multiplex PCR. Or we could do, if we choose multiplex, then it's going to try to design all the primers so they're compatible with each other and can work in a single reaction. If we choose batch mode singleplex, then what that does is allow you to get a single PCR assay for every single target. In this case, it would make 29 different PCR reactions for this HER2 and HER3. If I chose automated tiling, this is for when you have a single target and you want to have PCRs that are lined up one right after the other and design all of them to cover an exon, for example. I'm not going to cover that example any further today. I want to make sure we get through this multiplex. Then the detection type, you want to choose sequencing means there's going to be no probe design. If you want to design a TACMan probe, that doesn't make it any harder to do the design, but it will do both the primers and the probe if you do that. All right, the sequencing is the sort of typical mode that people use. Minimum amplicon gap means that the forward or the 3' ends of the reverse primer and the forward primer must be at least 25 nucleotides away. So all solutions that don't satisfy that are not going to be shown to the user. Maximum amplicon gap, 95 nucleotides. So if the gap is 95 nucleotides, and the total amplicon would be 95 plus the forward primer length plus the reverse primer length. So you get amplicons in this case around 140 nucleotides if you choose that. This is a setting that is a useful one to set to a bigger value. If you're not dealing with circulating tumor DNA, then this is something that, in order to give the software a little bit more program, a little bit more freedom to do the design, I would set it to 120 nucleotides. This next set, primer length range, this is also a sort of advanced user setting here. If you have a very AT-rich sequence, you know that it's AT-rich, then this setting of 28 is usually big enough, but if you have something really crazy, you can set that up a little higher, maybe up to 32 nucleotides. If you know that your target is very GC rich, then you might want to maybe set this region a little bit smaller than 23, down to 18 or so. But this range would allow you to sort of capture every possibility. The default settings work like 99% of the time, but sometimes you have an extreme target where it's useful to set those ranges a little different. I wanted to now show you just actually loading in that example. So I just opened up this file that had the 29 targets from HER2 and HER3. And it automatically processes it and asks us this question: do you want to combine or do you want to split? So there was just a few where it could have this choice, and I wanted to choose combine in this case. So when it did that, it took the 29 different HER2 and HER3 variants, and it combined them, and it automatically set up the forward primer range, the junction range, the reverse primer range. So these design settings are all there, and you can see which ones it combined. So it combined this 488 mutation with the 385 mutation, for example. So 2 of them are combined here. Here there was a cluster of 8 of them. Here's a cluster of 6 of them. Insertions and deletions as well as SNPs got combined here. But it was smart and combined them all in this sort of intelligent way. So next, just to sort of give you a sense, the sort of default settings we have here for the primer concentration, temperatures, and for the buffer, these are generally applicable, but if you have something in particular, your annealing temperature would be a particular one that folks would design. Maybe they do 60 degrees, some other number. Whatever your assay temperature is, put that in there. That was important. So the primers are designed to work at that 60-degree temperature. The probes we designed to work at the extension temperature if you had probes in your design, in this case 72 degrees. And then if you have tails that you want to add to each of your primers, you can do that here. If you have a universal primer sequence and a spacer sequence, you can, generally the spacer, we can't put in a random nucleotides for spacer. We just recommend putting in a bunch of A's. That's a way to run that. So you can put universal tails on your primers if you would like. Then going to the advanced settings here, there's lots of features here that are described in great detail in the user manual. So I'm not going to go through every single one of them, but I'm going to give you some highlights here of some things that are settings you might want to consider changing. So down here, the minimum Snip allele frequency, I told you we have it set to 1%. So rare SNPs in the human genome, anything more than 1% will be detected, and the primers will avoid that. If you want to set that higher, make it more permissive, you're welcome to do that. Or you can turn it off altogether by setting that value to 1. You set it to 1, then everything would be, it would just ignore the SNP. Some other settings here are a little more advanced. So this one, number of solutions to output. So some users don't want to get deluged with hundreds of different multiplex solutions, but we allow up to 254 solutions that you can output, and there's no extra cost in time. It does not any harder. It's just amount of output of alternative multiplexes that you can bear to see. So in this case, you can do 254 or 1. 1 is the default setting. Most people just want to see the best multiplex and try it, see what happens. Some other things here, this panel limit size. What happens is the space of multiplex, the number of possible multiplexes you can do, can be exponentially exploding. So if you have 100 targets, if I saved 10 different primers for each of those 100, then I would have 10 to the 100 power possible combinations. So we generally recommend using like 4. So this would mean for every singleplex in your reaction, you're going to save the 4 top designs, and those are candidates for multiplexing. If you find that your multiplex fails, like you try it and it just cannot find a solution to it, then you could set that a little higher. You could bump it up to 8 solutions per panel, but that will increase the runtime. Approximately, if you double the number of panel sizes here, you're going to double more or less the runtime of the program. Those are sort of the main features I wanted to show you from the regular PanelPlex.